the various.
Sorry, just make a record of your talk.
Okay.
Yeah.
Okay.
Yeah.
Okay. And then I'll talk about the various places where you can find coagulation fragmentation processes. Then we will talk a little bit about infinity itself. And then we will do a little bit of mathematics. I will actually write some equations, the pure coagulation equations, and also the Becker-Doring equations. And then what is interesting about this area is that, first of all, it's very useful, but also it has counterintuitive results. So things that when you see them the first time, they do not really make sense. So we will talk about two of them. One is gelation, and the other is the problem of equilibria in the Becker-Doring equations. And then we will make some remarks. The remarks will be to maybe to position my own work in this area, and to give you some bibliography and tell you who are the main contributors to this area of mathematics. So the area of mathematics we're really talking about is called the applied analysis, which is the applications of real and functional and also complex analysis to problems, problems in the differential equations, in some sort of the differential equations. Okay. Sorry. So the fifth element. So we made there are very many myths that many civilizations have, and in all those myths there is a sea, and there is a giant turtle that swims in that sea, and this turtle upholds the earth. And it doesn't uphold the earth all by itself. Here is the Akuparu from the Hindu myth, and on her back there are actually 4 elephants, and then you see that those 4 elephants are holding earth, which is rather flat in this one. That's a very beautiful picture. Of course, one could say this is not true. There is no giant turtle. There are no 4 elephants. But I'm not going to tell you what the giant turtle is. But I'll tell you that there is a way of interpreting the 4 elephants. The 4 elephants are actually 4 tremendously important partial differential equations. So all the Earth is actually all life, and everything that happens on Earth is actually based on those 4 equations, which are Schrodinger's equation, as you probably know, is the heat equation, the wave equation, and the Laplace equation. It's interesting that all those equations are actually linear. But I know personally people who say no, there should be 5 elephants. So there is another very basic type of equations that we should take into consideration. And those are coagulation-fragmentation equations. If you don't believe me that there are people like that, well, there is a book of Banasek-Lem and Lorenzo, and that's how it starts, by saying that coagulation-fragmentation equations are as fundamental as the 4 main equations of mathematical physics that describe a lot of the processes that we know. Now, coagulation-fragmentation equations, there are various flavors. So there are discrete ones, continuous ones, and then you can have the deterministic theories and also stochastic ones. And so we are going to restrict ourselves to discrete deterministic coagulation-fragmentation equations. And I'm going to try to convince you that they are really as important as the 4 types of the fundamental equations I've written there. Okay, so so what is it? What happens in the coagulation-fragmentation equations? We have systems. You can think about a cauldron, about a pot, and in it are floating molecules. And in those systems, we are therefore comprised of some basic units. So the building block of everything is something we call a monomer. And those monomers we can combine into dimers, trimers, N-mers, and so on. So you can think about monomers as being a polymer chain or a peptide or something like that. And then the difficulty of this theory is because we don't tell a priori how big N can be. So in fact, we're allowing N-mers of any size, right? And that's what is causing all the problems. We will talk about it in more detail. And in those systems of those floating units that can combine in different ways, there are two processes. One is coagulation, and the other is fragmentation. Classically, this is how we look at them. But of course, those processes can also be combined. And another problem in addition to the problem of not saying how big the clusters, the N-mers can be, is the fact that one of those processes is automatically, it has to be nonlinear. And so here we have systems that are infinite in size and at the same time nonlinear, right? So coagulation is the same thing as aggregation. We will show a picture in a second. And we usually consider only binary coagulation, which means only two clusters we can come together and then they give us a bigger cluster. So the picture is something like this. So on the left here, we have a four-mer, a tetramer, if you wish, and then the trimer, and they come together to give a seven-mer, right? So that's a classical coagulation process. And in the simplest case, we always think that there's only one type of a seven-mer that a four-mer and the three-mer can give. And the important thing to understand that in this aggregation process, no mass is lost, right? So if the unit of a monomer is, if the mass of a monomer is 1, then the mass on the left is 7, it's 4 plus 3, and then the mass on the right is also 7. Okay, so this is the coagulation. And coagulation is nonlinear because the rate of such a process, by the laws of chemical kinetics, depends on the concentration of the four-mers and the three-mers on the product only of the concentrations. And that's clearly a nonlinear term. We will write down the equations later on. Okay, so coagulation equations were considered first, and they made the usual coagulation equations are called also Molokovsky equations to honor the person who invented them, who was Marian Molokovsky, a very famous Polish physicist, who unfortunately died from dysentery at a reasonably young age. So when we hear Molokovsky equations, be sure that you know that we're dealing just with pure coagulation equations. There is also fragmentation, which is the opposite thing of coagulation. You take a large cluster. In this case, again, it is a 7 cluster, and it can break into bits. When we were working with discrete equations, the smallest unit into which it can break are 1-mers. When we're working with continuous equations, the smallest bit can be as small as we wish, positive size or mass. So in this case, I'm looking at the ternary fragmentation. In the so we from 1 7-mer, I got three smaller clusters, but in the equations we will look at, we will only consider binary fragmentation. Okay, so we mean, and again, the important remark is that the mass is conserved. There is no growth. There is no loss of mass at all. So we have 7 on the right and 7 on the left. The theory of coagulation-fragmentation equations can incorporate much more complicated mechanisms of aggregation and breakdown. So one of the applications of this theory is to grinding mills. So the grinding mills are a kind of long pipe with a screw. You put in a heterogeneous collection of rocks on one side, and on the other side, hopefully, you get pebbles or pieces of rocks that are more or less of the same size, and it's very important to grind them down to a particular size. So what happens inside the grinding mill? It is, of course, pure fragmentation, but it is a very complex, nonlinear type of fragmentation. So an example of a process which is a reasonable process for a grinding mill is something like this. We have a large rock, which is here represented by a 7-mer. The large rock hits the smaller rock against the rotating screw and breaks it. But maybe you can think about it as a 7-mer coming together with a 3-mer to form a 10-mer, and then 7-mer, there's nothing happening to it, but the 3-mer breaks down into a monomer and a dimer. Of course, there also be very interesting shattering processes, in which case you have 2 large clusters that collide, and both break up into monomers. Those shattering processes have a very interesting non-trivial dynamics, if you also allow for the coagulation. So I hope it is clear what kind of processes we're looking at. And the point is that those very simple processes of the coagulation and the fragmentation occur in an enormous variety of natural phenomena, and the natural and also industrial phenomena. So I don't know if those processes are the equations are the fifth elephant, but certainly a case can be made for them. A very important particular process which occurs in modeling of the liquid gas, the liquid vapor transition is a very old model due to Becker and Doering from 1935, which is a very limited type of coagulation and fragmentation in which everything happens by adding and shedding exactly one monomer. So here we have a K-mer, that combines with a monomer to give you a K+1 mer, and this K+1 mer can break again into K mer and the monomer. So to exhibit the whole richness of the CF processes, the Becker-Döring equations are not enough, but they already are show some very puzzling properties. And also the Becker-Döring equations are a good test bed for trying out mathematical techniques. So if a mathematical technique does not work for the Becker-Döring equations, then it won't work for the more general coagulation-fragmentation equations. Just the fragmentation by itself is usually very easy, but the moment you're including the coagulation, those are genuinely very hard equations. So let me just tell you about the different applications of the coagulation-fragmentation equations. It is really enormous. It spans anything you want from medicine to astronomy. So there is quite a lot of interest in people who are modeling Alzheimer's because there we have peptides, the beta amyloid, forming complexes that are not the ones the body wants. So if you have a badly folded beta amyloid peptide, it can be, by coagulation, create enormous complexes of beta amyloid that are misfolded. Same story with prions, which are the cause of the mad cow disease. Very interesting things, prions, because it's not clear in what sense they're alive, but they are a kind of self-replicating thing. In polymers and in the aggregations of colloids, so the curdling of milk is a coagulation process. Of course, in aerosol dynamics, in aerosol we have the drops of liquid that collide, that can combine. Recently, there's been beautiful application of the CFEs to the dynamics of fish schools. So the fish baby who swim in an enormous school can separate, the different schools can combine and so on. I'm not going to show you pictures of those ones, but we will show you some pictures of the two last applications. Coagulation-fragmentation equations are used in astronomy, in the theories that explain how planets are formed, and probably industrially the most important application, and very much of my own work is in modeling process connected to molecular beam epitaxy. I will show you in a second what that means. But first about the planetoid formation. So here is something about news from 2013. So people saw using the telescope in Atacama, which is a desert in Chile. They saw a region around the young star where dust particles can grow by clumping together. Growing by clumping together is precisely coagulation. And they also modeled it, and so it solves the model, I guess, along the extending mystery about how dust particles and disks grow to larger sizes so that they can eventually for comets, planets, and other rocky bodies. And one of the reasons I read it out is because there is a philosophical question there. How looking at something and modeling it actually solves a mystery. This is something you should think about. What exactly does mathematics do? And if I have to tell you what is the turtle, well, the turtle, of course, is mathematics itself. Okay, right, and then here is my molecular beam epitaxy. So molecular beam epitaxy is the way we construct nanomaterials, smart materials, and so on. You have a table, which is this square board, and then you have a gun, and from this gun, you're shooting atoms, for example, gold atoms or something like this, onto the surface. So that's called the deposition. Then when some of the little atoms they run about, and when some number of them, which is called the critical nucleus number I, come together, there is a nucleation, and they form a immobile island. Of course, they can be dissolve and evaporate, which is fragmentation. But also, once you have an island, the island can grow by capturing another free-floating atom, right? So those atoms that are by themselves and run around on the table, they're called atoms. And if you think about this, this is a sort of a Baker-Doring process, except that for nucleation, you usually need more than one atom to come together. For example, in graphene, you need five atoms to come together. Okay, and then, as I said, very much of my own work is doing the coagulation, the fragmentation for molecular beam epitaxy with colleagues in chemical engineering. Very interesting process, and it's tremendously important to have very good control on those islands, how big they are, how regular they are. For example, I'm sure I have heard about quantum dots. In quantum dots, you want them regularly spaced and having the same size. Okay, so all those are clearly the coagulation fragmentation processes. Right. So you might ask the following questions. So what is it one wants to know if one wants to work in coagulation fragmentation equations? So people who work in this area are physicists, chemists, and mathematicians. The mathematicians are usually people who know a lot of real and functional analysis. Complex analysis as well, I didn't try that. Asymptotics. Of course, it is very closely connected with the theory of partial differential equations. You have to know the dynamical systems theory, and it is not at all a bad idea to be good in the probability theory as well. Probability theory, of course, deals with its own problems, but it also provides a lot of very good techniques outside of the probability theory itself. And what I have written there in red are the things that I myself use. So the most interesting tool I use is from dynamical systems theory, something called the central manifold theory. And the reason, the main take-home message is that the theory of coagulation fragmentation equations contains counterintuitive results. And I think the community of people who work in the CFEs have not really explained, at least they haven't explained to somebody as dumb as myself, precisely what those results mean. I know what they are, but their physical meaning is not at all clear to me. And those results, as I already said, they have something to do with the fact that we were working with infinite systems. And if you're not sure how counterintuitive infinity is, I very much recommend to you, you read about the Hilbert Hotel, right? The Hilbert Hotel can be full. It's an infinite hotel. It doesn't have 10 million, zillion, quadrillion rooms. It has an infinity of rooms. And a hotel with 10 million, zillion, quadrillion rooms can be full. It's possible to fill it and not to have a single room that is vacant. But the Hilbert Hotel can never be full. Because if it is full, and another person arrives, you just move the person from room 1 into room 2, the person from room 2 into room 3, and so on. So it is a very good check on your intuition. I think our human intuition doesn't really work with infinity. So this is something I recommend you read about, and there is a very nice URL you can consult. Okay, so let us now write some equations. And so we have k-mers, and what really we want to write is the equations for the evolution, for the dynamics of their concentrations. And let us denote the concentration of the k-mers by ck. And so we want to understand how ck varies as a function of t for k going from 1, 2, 3, 4, 5, and then and as I said, it is up to infinity. So every possible number k is allowed. So then, as I said, we use the laws of mass kinetics, and then the general general discrete coagulation equations, Molokovsky's equations, have the form. So for ck, for the rate of change of ck with dt, we have two terms. The first term takes into account the coagulation of a j mer and then the k minus j mer, which coming together gives you a k mer. So that one has a plus sign. The constant a, the j k minus j are positive constants. And the second term is the rate of decrease in the concentration of ck during due to the coagulation of ck with other clusters. So you see those are quadratic terms. So that's an inherently nonlinear equation. And then the similar equation for C1. So for C1, we of course in the simple equations we have no source of it, so we're only just using it. Okay, so those are the equations, and when people see them for the first time, they're usually very confused by the 1/2. Okay, I'll talk more about the 1/2 there. So in those equations, there are very many things to think about. From now on, every time you see something written in blue, this means that this is a question that you should explain to yourself. After the lecture, I will correct all the mistakes I can find. So far, I haven't found any. And then I will send the lecture to Professor Litvinov. He will put it online, so you will be able to play with the blue questions. So explain to yourself the 1/2 factor. I will do it in a second. because I think this is an important point. So what is the mathematical object? The mathematical object is an infinite set of ordinary differential equations. And so what do we mean by a solution? Again, we mean an infinite vector, C1 of t up to Cn of t and so on. And by looking at it, just by looking at the equations, you should understand that it cannot have any equilibrium solutions. So that's not a difficult question. Just look at it and you will understand. When you look at what exactly is happening, okay, those are just binary collisions. So the mass is not lost. So formally, without thinking about convergence of infinite series, it looks as if all the clusters are accounted for. And so you would expect that the mass, so we will call M1 because this is the first moment of the sequence CK. The mass which is just the sign k goes from 1 to infinity of k ck of t, you would assume that it is conserved, which means that the derivative of the mass with respect to time should be 0. And that is not the case. That is something that is tremendously counterintuitive. That in fact, you're losing mass. And that's another take-home message that such things can happen, and they can be proved. I'm not sure they are quite explained. Sorry, so if you go back to those equations, the properties of those equations depend crucially on the assumptions you're making on the coefficients a jk. So a jk is the rate at which a j-mer collides with a k-mer, and for different contexts, the physics tells you that the dependence has to be of a particular type, and in general, the faster the faster AJKs grow with A and J, of course they must be symmetric, right? AJK and AKJ is exactly the same thing. The faster they grow, the more pathological are the solutions, the behavior of those equations. Okay, and so the main questions, the main mathematical questions that we ask are precisely what is happening to the mass, and what do solutions do as the time goes to infinity. This is called the asymptotic behavior of solutions, and I'm not going to talk too much about that. There is a beautiful theory of what's called similarity solutions. So this is the 1/2 factor. Let me give you an example and how to explain it. See, suppose we have a finite system. So the largest n-mer we can have is a 4-mer. Then just looking at the reactions and using chemical kinetics, we get the following 4 equations. I will just explain the first one. The first one says that the dc1 dt is -2 times some kinetic constant. Why is there a -2 there? Well, the reason is that for each time this reaction occurs, 2 C1s combine together and give you a C2. you're actually losing 2 molecules of C1. At the same time, the same reaction in the second equation gives you only 1 molecule of C2. So that's why there is a minus the 2 there, but on the next line there isn't. You're also losing the 1 molecule of C1 that combines with C2 to give you C3. And you're also losing 1 molecule of C1 if it combines with C3 to give you C4. And so you argue all those 4 equations in that way. And then you can see that the mass is conserved. So the mass contained in the C1 is just C1. The mass contained in the C2s is twice C2s because each molecule, each dimer has the 2 monomers. So you can check that this is correct. And now if you want to take those equations and put them in the form I gave you before, just put kk is equal to ak divided by 2, and akj is equal to ajk is equal to capital akj. That's a very nice exercise, and also it shows you that in the final system, in the finite system, that there is nowhere for the equations for the mass to run away. And if you think about the system, what happens that everything is coagulating everything is collecting itself into C4s. Of course, if you allow an infinite number of complexes, can be transported to infinity. All right, and so let me also tell you what the Becker-Doring equations look like. There's a very nice way of writing them. So if you look at CK can be obtained from CK minus 1 by combining with C1, and it also, right, there is a mistake here. This should have been multiplied by CK plus 1, and it can also be obtained by fragmentation of CK plus 1, and it is lost through fragmentation of CK, and it is also lost by coagulation of the CK with K1 with C1. So you can write it in a very nice way in terms of fluxes. If you call this quantity the flux JK, then those equations are written as JK minus 1 minus JK. And for K is equal to 1, we certainly can also write that this is minus G1 minus JK. So those are equations with both fragmentation and coagulation. Right. So from now on, I'm going to show you 2 results that are very that are very counterintuitive. So first of all, let us consider the pure coagulation equations. So those were those ones, right? Just the coagulation. With what is called a product kernel. So JK is equal to J times K, and you might ask me, does this happen in physical situations? Yes, it does. This is a suitable kernel for branch polymerization. So it happens in chemistry. And in this case, we have an infinite system of nonlinear equations, but we're very lucky in that there is an exact solution. So the exact solution is what's called monodisperse, which means we start with only monomers. So we C1 at 0 is equal to 1, and the CK at 0 is equal to 0 for all the rest. And you can work out an exact solution in this case. And it is quite a bit of mathematics to work out this exact solution. And I'm just mentioning the techniques one needs. One needs the idea of a generating function. For this generating function, you derive Berger's equation. Then you solve the Berger's equation with the method of characteristics, and then from it you need by Lagrange's inversion theorem to find the formula for C K of t. And this is what the functions look like. They look one way for t less or equal to 1, and they look a different way for t larger than 1. And now watch, for t larger than 1, there is a t in the denominator for every k. That means that when you write the formula for the mass, the mass will be some number, which is actually 1, as you're welcome to show, divided by t. So that means that for t larger than 1, we're bleeding mass. It's the mass of the system is decreasing. And if you're really thorough, you might want to show that for every t less or equal to 1, the mass of solutions given by this formula is actually 1. So this means up to t is equal to 1, the mass is constant, it is 1, which is precisely what we have started with. And then it starts going somewhere as 1 over t. And so it is a good exercise to check that everything I'm saying is actually correct. Right, yeah. Now the interesting thing is that we can compute the second moment, which is the sum k goes from 1 to infinity, k squared, the ck of t, and then you find that it's given by the function 1 divided by 1 minus t. So it actually blows up at that time is equal to 1. So t is equal to 1 is what is called adulation, and this strange phenomenon of losing mass. Sorry, the t is equal to 1 is what's called the adulation time, and this phenomenon is called the adulation. It was discovered by physicists. I'll mention their names. And in the interpretation, it doesn't quite make sense to me. It means that this mass is lost to the infinite cluster. This infinite cluster is not something the equations taken into account. So it's a kind of gel. It is formed in the system. And a general remark is that it's actually very beautiful to have an exact solution. And a friend of mine, a very good mathematician, Viktor Galaktionov, once said that exact solutions are windows into the nonlinear world. They're explicit. You can examine them, interrogate them for what they do. They're absolutely invaluable. So depending on how fast those coefficients a, k, j grow with k and j, you can prove that adulation has to happen. And there are cases if they grow too fast, very fast, then adulation happens from time is equal to 0. From the very beginning, it's called instantaneous adulation. From the very beginning, you're losing mass. So that is very puzzling. And the most puzzling thing is that this product kernel is actually physically very reasonable kernel. All right. So the second question is about, so we're now on a different problem. And in this problem, what happens can roughly be described by this picture. In this picture, you see a jar standing on the wall, and then there is a basin, only the vertical part of the wall, and then there is a slope going to infinity, going forever. The slope is going forever. So what happens here is that if the volume of water inside the jar is less than the volume that the basin can take, so if V1 is less or equal to V2, if you pour the water into the basin, all of it will stay in the basin. But if the volume in the jar is larger, then the volume V1 minus V2 will spill over, and it will run off to infinity. So this is something that actually can happen in the Becker-Doring equations, and I will show it to you very quickly because we have very little time. So suppose we have a system of the Becker-Doring equations which can be written in this way through the fluxes, and suppose the initial mass is M10. It is some finite mass, and we want to understand what happens to the solutions as the time goes to infinity. Right. So in this case, it is very easy to find a formula for the equilibrium. At equilibrium, each one of those right-hand sides must be 0. But the first equation means that each one of those fluxes must be, sorry, so all the fluxes must be equal, but each one of those fluxes must be 0. So then there is a very nice formula in terms of the equilibrium concentration of the monomers, which I call Z. Then you can define the coefficients Q sub k through the A's and the B's, and iteratively you find that the equilibrium mass is given by this infinite series. And so everything depends on the convergence of this infinite series, or more precisely, only the solutions of the equation that an equilibrium mass is equal to the initial mass. And of course, this function M1 echo of Z is a monotone function of Z because all the coefficients are positive. So there are actually 4 different cases that can happen. We let R be the radius of convergence of that series. So there are 2 very tame cases. One is that R is equal to infinity, and the other is that R is less than infinity, positive, but less than infinity. But the limit of the equilibrium mass is infinity as Z goes to its radius of convergence. In this case, there's nothing special. All the solutions of the Becker-Doring equations go to the unique equilibrium having the same mass as the initial data. So when they say they go, they converge in some sense. So you need to set up a Banach space where solutions live, and this is the Banach space. It is a weighted little L1 space. Yeah. So without the K, it would just be the little L1. But this is a weighted one, and so the saying that something converges to something else means that the norm is going to zero when time goes to infinity. So in those two cases, there is nothing special. The special cases are the 3 and 4. I'm not going to tell you what is the case 4. There is a reference, but it is a nice question. So the interesting case is where the radius of convergence is finite, but the limit as z goes to its radius of convergence is also finite. Call it the critical mass. But of course, before you want to analyze, to analyze it, you should ask, is it actually possible? Yeah, so here is an example where all the AKs are constant and the BKs are bounded. Yeah, we bounded in this way. So then R is equal to B divided by A, and the critical mass is the 2B divided by R is the B divided by A, and the critical mass is 2B divided by A. So the exciting thing is if the initial mass is actually larger than the critical mass, that means that there is no equilibrium for the solution, no equilibrium with the same mass as the initial data for the solution to go to. That's exactly like in the jar and the basin. So what happens here is that actually the solution converges, and then everything here converges with quotation mark to the critical semi-equilibrium solution, which is the R Q2R squared, Qn Rn, and so on, which actually has smaller mass than the initial mass, right? And the interesting thing is that this is not the same convergence as before. This is component-wise convergence, and the mass is the same as the initial mass for all time. That means that this convergence cannot be the usual strong convergence as before. So what happens here is that the excess mass is being transported away to larger and larger clusters, and this type of convergence is what's called in functional analysis weak convergence. So in my drawing of the jar and the basin are not quite, they do not quite capture this weak convergence, but I do not know how to draw a better picture. So that's basically another very bizarre result. There is this weak convergence to an equilibrium that has smaller mass than your initial mass. All right. Okay. So let me just say a couple more things. So the most important contributions to this theory have been of the physicist Oliver Penrose, who is the brother of Roger Penrose, who convinced excellent mathematicians, the John Ball and Jack Carr, to work in this topic. Levraz and Ziff are our physicists, the fundamental in getting us to understand gelation. Philippe Lorenzeau, Barbara Niethammer, and Bob Pego are the next generation mathematicians who are right now pushing this theory forward. There is a new book about the coagulation-fragmentation model. So it's about continuous equations. We very much recommend it. Wilson Lamb is one of my co-authors. And there are two very good reviews. And if this area interests you, I really recommend you have a look at the Jonathan Wattis's review from 2006. It's not very mathematically intense, and it is very clear. All right, just to finish. So all my papers on the CFE are basically on MD. What I wanted to do originally in this lecture is to show you how to model a disease, silicosis, by using the coagulation-fragmentation equations framework. And then I realized that this is actually the wrong framework. So there is an archive preprint, which is given here, which shows you the reasoning why this is the wrong the wrong model. And so the correct model is actually a transport equation coupled to an integral differential equations. It's a very active area, and I think that where the area is moving is to coagulation fragmentation equations with complex dynamics, like periodic motion, chaos, various reduction principles. Against I recommend you have a look at central manifold theory, which is beautiful, quasi-steady state assumptions, connections with chemical reactions network theory. Those are just infinitely dimensional chemical reactions. New similarity solutions, convergence rates to those solutions, and of course, new applications. And that's me. Thank you for your attention.
17 hours.
Thank you very much for your very interesting talk. So any questions or comment or remarks? I think something from chat we see. So maybe I ask a question. So Professor, do you have just pure fragmentation equations?
Yeah,
I discuss about this pure,
for example,
yeah.
Yeah, the grinding mills, the pure fragmentation, but their pure fragmentation, which isn't linear.
Mm-hmm.
And it is an active area in the engineering. There's a lot of money in those grinding mills, and there's a lot of literature on what is the right way of writing fragmentation. In the linear fragmentation for discrete coagulation fragmentation equations is absolutely trivial because everything just goes into monomers, right?
That's right. Yeah.
It is. If you have a continuous system, then there are various problems of losing your mass to dust, to infinitely small particles, exactly the opposite of the
Coagulation.
coagulation. But I think because coagulation is much more mathematically difficult, much more work has been done on the coagulation, but shattering as well is actually a coagulation process. Sorry, a fragmentation process. The work on shattering.
Right. Yeah, that's very interesting. Yeah. So any other questions or Yeah, Elaine.
Thanks. Michael, could I ask a question about the bit at the end? Sorry, I have a strange echo. When you say that people will be interested in the complex dynamics, is there a particular area of applications where you think the study of complex dynamics will be really important?
Yeah, so there is a new paper by Bob Pego.
Mm-hmm.
At this stage, it is only for finite size. So he doesn't work with infinite size systems, but there's some physically very obvious mechanisms where periodic motion can happen. So the periodic motion can happen in a coagulation fragmentation equation in which you have coagulation of some sort, and then you also have shattering, which with two big clusters breaking into monomers. So you can see how it works, right? So they break into monomers, grow big enough so that they have enough energy in some way to collide again and break again. I think in Barbara Niethammer's work, there is also physically motivated systems with complicated dynamics. But I'm not sure about chaos, but the periodic motion proving the existence of bifurcation and so on. Michael Velasquez is working on this as well. That is definitely an emerging direction. But yes, it has physical motivation, it has real mechanism behind it.
Thanks.
So any other questions?
So
yeah, please, Michael.
So there are two or three things I noticed, and maybe I will correct them and I will send to you.
Yeah. So if no further questions, let's thank Professor Grinfeld for this very beautiful talk again. Thank you.
Thank you very much.